Hi, I'm Jamie. This is Dead Dodge Garage, and this is a 426 Hemi. Again! I've actually done a few videos on this project up to this point already. In the last video, I showed the freshly machined block, the new clean heads, all the components we've got, and I started going through the things that are going to be going into this engine. What I didn't do is actually start building it at all. In fact, at the end of that video, it went back to the machine shop because the cylinder heads didn't fit. Well, now it's home, and the cylinder head issue is fixed, which I will demonstrate in just a minute here. So today, we're going to go over some things, and then we're going to start actually putting this Hemi together, which I, for one, am very much looking forward to. Now, as with just about every single build we undertake here, I don't have everything under this roof right now to fully finish this engine. I've got most of the stuff. I think we have everything for the short block, so hopefully we can at least get that far today. The engine build pile around here is getting absolutely ridiculous. We've got 3 sets of heads right here, 2 sets of pistons, cams, rods, too many things. Relocating part of this ridiculous pile, we find our glorious 426 Hemi heads and our sandblasted intake manifold, which kind of has some stuff stuck to it. Gonna have to deal with that at some point. Here are those glorious and ridiculously heavy heads set in place on our block. Notice they actually fit now. Yay! I actually test fit these last week when they first got back here just to make sure I was satisfied with them, and I am. We'll look at the undersides in a second here and you'll see what I'm talking about. Note, I do have these numbered. This is cylinder number 1. This is cylinder number 2. I did that because they fit better this way and I don't want to get them mixed up. I learned on this 426 teardown a few weeks ago that major issues can arise if you get this wrong. See, typically you'd expect these heads to be ambidextrous. The fit should be the same and you should be able to reverse them. On this engine, for whatever reason, the chambers were nowhere near centered with them flipped odd head for even head. And we know they were flipped because the ports were actually numbered on these heads. In that video, I flipped them side for side and it was immediately apparent that the fit was much better. The chambers were maybe not perfectly centered, but they were much closer. Probably close enough to prevent the piston contact that this engine had been experiencing in the past. In past builds, I almost never checked this kind of thing. But it has become apparent the more I do it, particularly looking at these 426 Hemis and slant 6s of all things, that it's important to check. And so moving forward, I'm always going to dry fit heads like this. Anyway, we're looking up to the odd side cylinder head now. This is actually cylinder number 3. Here's cylinder 1. What we really want to see here is uniform exposure of the flat part of the cylinder head around the chamber for the entire circumference of this cylinder. And it looks like we've kind of got that. Of course, my flashlight is kind of moving reflections around and it's hard to be sure, but looking at this with the naked eye, it sure looks like they're pretty well centered. Take number 7 here. You can see that shiny ridge all the way around the cylinder, so I feel good about that. Here we're looking up into cylinder number 6 on the opposite head, of course, for an example of something not quite so good. Note there's a whole lot more shiny at the front compared to the back. This entire chamber is shifted rearward relative to the cylinder. Number 4 is similar, maybe a little less obvious though. Number 2 is even closer to centered. Number 8 looks about the same as number 6. You can actually tell just by looking at how these heads sit on the block that this head is further back. It's pretty obvious actually. But flipping this head to the other side did not improve that. In fact, it made both sides worse. So we're just gonna have to go with this. Obviously this isn't perfect and I'm not exactly in love with that, but there's nothing we can do about it at this point. The good news is the chamber is not massively shifted over. We do see that shiny all the way around the outside, so that tells me it's close enough that everything will probably be fine. Here's another head fitment issue. I pointed this out in the last video, but you can see that overhang. This is due to the deck surface having been machined pretty significantly at some point in the past. That moves the entire head down this way, and because these surfaces weren't cut to match, that corner doesn't line up. The big problem with that, of course, is intake sealing. Look at that gap. Typically, when you dry fit an intake in heads like this, the two should touch. And in this case, we have gaps on both sides. This is a factory dimension Felpro intake manifold gasket. It measures 60 thousandths thick. Currently, in this gap, it's kind of a hot dog in a hallway type situation. Over here, it's kind of sort of a snug fit. This is one of the gaskets I took out of this engine. So the question is, how did this ever seal? Did it ever seal? I don't know. I had an intake fitment issue on this 451 stroker engine in a very similar way. This wasn't because of deck surface machining. This was because of a factory drilling error. The dowel pins and all of the bolt holes were actually shifted that way on the block. So I had to shim this valley pan and intake to close up that gap. Essentially, we're going to have to do the same exact thing here. Now, Mopar Performance used to sell a thicker intake manifold gasket. It measured about 120 thousandths. That gasket is no longer available anywhere that we can find. So what we're probably going to have to do is double up on the Fel-Pros and silicone the whole mess together. I can't say I'm excited about that, but we don't have many other options. So that pile of intake gaskets is one of the things we're waiting on right now. We won't have an intake final installed today for sure. With all of that figured, I've got the block upside down again, and it's finally almost time to install the crankshaft. First, I do need to go through a quick round of cleaning here. Now, if you know these engines well, then you know the basic bottom end architecture is exactly the same as a BRB engine. Of course, the bearings are a different size in a B engine, like a 383 or a 400, but they're the exact same in a 413, 426 wedge, or a 440. The main caps are the same design, and the only difference, the 426 Hemi has those cross bolts. The cross bolts were added because this engine was originally designed to be run in NASCAR, and at screaming high RPM for extended periods of time, these main caps would walk back and forth. The cross bolts locked them in place and prevented that. Cleaning the block now, here's all of the grime I wiped out of the bores and the inside of the block. There's actually a little bit of metal on there too. You definitely want to do this before you start assembling your fresh engine, even if it did just come back from the machine shop in a bag. There's a reason I wasn't very good at basketball. Clevite main bearings. These are a 10 undersize to match our crank. Note, these are high performance, fully grooved bearings. This isn't even just a pair of top shells. There are some with holes and some without holes. In case you have any questions about how necessary it is to clean off all of the new parts before they go in your engine, admire this grime I just wiped from the brand new top shell for the thrust bearing in this thing immediately after removing it from the factory plastic. Clevite bearings always have a date code. This one is dated 7 of 24. That's July of last year. So whoever looks in this engine in the future, maybe me, will know when it was rebuilt, roughly. The best advice I could ever give a prospective engine builder is clean everything and scrutinize every single piece. I promise you I'm taking that to the extreme on this one because this isn't just some big block. It's a Hemi. Example. The last set of RB engine main bearings I took out of a box and tried to install in a block did not fit very nicely. The thrust shell in particular just kind of moved around. These ones fit well, which is good. If they didn't, we'd be hunting for replacements right now. Here's the grime from our freshly polished Hemi crank. I really like using those blue towels, but they do leave behind a little bit of lint, so you have to be mindful of that. Main caps. Weeks ago, I was assembling a 440 bottom end, and I found an issue. That issue was the thrust bearing, the number 3 main bearing, would not fit tightly in the cap. I went and dug up another set of main bearings on the shelf that happened to be the right size, and the one out of that box fit perfectly. This is the shell that did not fit properly in that 440. Check this out. It's a Clevite with a build date of 4/24. This is a Clevite in the 10 undersize with a build date of 4/24. So I don't know what they were smoking at Clevite on that day, but they didn't know how to make 440 10 undersized main bearings, I'll tell you that. So now I'm digging through all our spare Hemi crap. We actually have a surprising amount of spare Hemi crap. There are some bearing sets in here, but I don't know if I'm going to find 10 under mains. Dang it, here's a set of 10 under mains, but it says 340 318 on it. Not helpful. Another set of 10 unders, but certainly not Hemi size. The bearings I need could be back here. Somewhere. Nothing. Screwed again. Why does everything always have to go off the rails? I don't know, it just do. I did decide I'd get the other caps prepped and put in place. I've only just noticed 2 of the main bolts in this thing are shorter than the others. Oh, and this one's longer, which is almost weirder. Now here's something peculiar to the Hemi and that has me a little bit worried. See, these main caps with the crossbolt sections need to be tapped home. I always install my main caps with a hammer, lightly. In this case, because these tabs for the crossbolts have to squeeze between these protrusions, you have to start tapping a lot sooner. I can just barely get these main bolts in 1 thread or so. And as I'm tapping this down, I might be worried that the main bearing shell shifts around or something. All right, that wasn't so bad. Now I've just snugged those bolts on the number 2 main cap, and the crank spins very nice. I backed the main bolts back off and wiggled the cap a little bit so I could get the cross bolts in. These bolts do locate the cap, kind of, but there is actually a gap around them, and so the cap can shift this way ever so slightly. With those loose, wiggling the cap just a little bit helps to get the cross bolts in. With those cross bolts just touching the block, snug but not tight at all, I tighten these bolts back down. I will need to final torque these, and then I will final torque the cross bolts at the end of that. I'm going to tell you something now, so we'll both know. The number 4 cap does not press into its register. It just kind of sits there, and I can slide it front to back a little bit. I don't love that, but I'm going to be torquing it down anyway. Hey, we've got cross bolts to help keep it from moving. That's the good news. It's a little late in the game to be really worried about this. And remember, this will never see screaming high RPM or a drag strip or anything like that. It will get driven on the street though. Did I mention that I did install the top half of the rear main seal before I dropped the crank in? Well, if you're going to build an engine, make sure you do that. I also greased the sealing area on the crank here. Still spins very nicely with the number 4 cap run down. And there's the number 5 in place. That one did register correctly, and the crank still spins very nicely. I did have one issue, though. Remember that whole longer and shorter main bolts thing? Well, one of those longer main bolts was in that number 5 cap. It would not bottom out. It actually stopped spinning and came up super tight right about here. That super long one is on the number 4 main cap, and it fit without issue. I don't know why there would be different length main bolts between the various caps. I don't know which spot those came out of. I pointed out these fully grooved main bearing journals on the crank in the last video. At least one commenter said that's not a good idea because it weakens the crank slightly, and that makes sense to me. I've never seen another crank done like this, and I don't expect I will again anytime soon. As you can see, it lines up with the groove in the main bearing. Because this thing has fully grooved bearings, the groove will be aligned with that groove all the way around. Essentially what it does is kind of almost doubles the volume of oil that'll be stuck in there. That's just allowing for extra lubrication to go through this feed hole out to the rod bearing. That's the purpose of doing this. There will be more oil available to these rods than if just the bearing was grooved, and much more available to them at all times than if only half of the bearing was grooved. You see, with the typical half-groove bearing, that hole for the rod bearing oiling is only exposed to that groove half of the time. When it's in this area, it's covered up. That essentially means there's only pressurized oil flowing out to these rod bearings about half of the time. And so I'm sure the thinking behind grooving these crank journals is it further enhances the amount of oil that's able to get to these rods. If you know Hemis, then you know the rods tend to exit through the side of the block, so I'm sure they were trying to avoid that at all costs. I'm not saying you should do this. Off camera, I custom file fit every one of these rings to every cylinder using the specs provided on this Hastings chart. I believe that was 19 thou for the top rings, and they actually specified a wider gap for the second ring. I think it was 21. Anyway, these are ready to assemble. I did put the pistons on the rods and installed these annoying circlips. Remember, these are Racetech pistons. They're essentially a street Hemi piston design, although they're slightly more modern looking. And these are factory rods that were ground and polished at some point in their history. They do have brand new ARP hardware. I'd start putting these together now, but it's like go home time, and there's no point anyway because I can't install them. So we'll get back to this at some unknown point in the future. It's a week later or something, and I have some new insights on this bearing fitment issue. Our local machine shop, Johnson Machine, has done all of the background work for every shiny new engine I've ever built. And I trust their judgment on things, so when I discovered this issue, I gave them a call and asked. Essentially what I was told was, yeah, it should fit tighter, but the crush built into this bearing will expand this shell and force it into the housing, resulting in the correct clearance once these bolts are torqued down. Or that's the way it should work anyway. Essentially, all I need to do is measure this oil clearance, which is a good thing to do anyway. And if it's correct, well, we should be good to go. There are a couple different ways to do that. The first way would be to take this all apart and use a bore gauge to measure the inside diameter of this bearing once the cap is torqued down, then measure the crank journal and compare the two to find the oil clearance. As I've discussed in past videos, I'm terrible at operating those measuring devices, and I probably wouldn't come up with a reliable result anyway. Instead, we're going to try and do it the quick, cheap, and easy way today, using something called Plasti-Gauge. This is a little rope-like material that you insert between the crank journal and the bearing shell. Then you torque the bearing shell down, untorque it, pull it back out, remove the Plasti-Gauge, and compare it to your chart here. I've got Plasti-Gauge in place across the bearing, and I've got the cap torqued in position now. Here's your bi-weekly reminder that one of the things that makes the 426 Hemi so beefy and great, these cross bolts for the main caps, makes these like impossible to remove. After quite a bit of frustration, I got the number 3 cap back out, and we can see here where the plastic gauge ended up squished in place. You can see the original size there, where it was not crushed between the journal and the bearing, and then you can see how far it spread out right here. All we have to do is hold our gauge up to that, and we'll see how big the clearance is. Now the green stuff, which is what I'm using here, can measure between 1 and 3 thousandths. That's a pretty good range for an oil clearance on this main bearing. That's the 3 thousandths gauge. It's a little bigger than that. That's the 2 thousandths gauge. It's a little bit smaller than that. So I'm gonna say we've probably got about 0025, I guess. Somewhere right in there. That's definitely a safe clearance. So I think we're good here. The bad news is now I gotta clean this garbage. Now again, just so we all understand, because we got a good oil clearance there, that means this bearing is crushing the way it should, and we can therefore infer that it's filling the cap as it does that, and we should be perfectly safe here. I still don't love it, but we're going with it. Let's put this thing together. Got that all cleaned up, pre-lubricated the bearing in the journal. I've got the number 3 cap back in. The cross bolts are in there, again, just snuggish, so the cap can still move up and down. And now I'm setting the thrust. I've got a screwdriver forcing this counterweight forward carefully. I'm gonna torque this middle cap to the first stage. We'll pull that out and then measure how much end play we have on the crank. So I actually had to take 2 stabs at this. Typically what I do is send the crank forward, torque the cap down, and then check. When I did that on this one, I had 2 thousandths of end play, which is nowhere near enough. So then I loosened this and instead pried the crank rearward, moving the thrust surface that way. I'm assuming that this shell was offset from the upper shell in the block a little bit. So by moving it rearward now I have, I think it's 7. Let's see if I can show you that. There's 0. There you go. 7 thou. Your typical range for acceptable crankshaft end play is 5 to 10 thousandths. At 7 thousandths, we're right in the kill range on that, so I'm pleased. Now I'm going to come through and torque all of these bolts properly, and then I will torque the cross bolts, and the crankshaft is done. The main cap bolts, despite being almost the same as a BRB engine, are torqued to 100 foot-pounds in the 426 Hemi instead of, I think, 85 in the typical engines. These side bolts are torqued to 45 foot-pounds. I haven't done that yet, but all of these are torqued to spec. And it spins really nice, so I feel good about that. Here's the thrust. I don't know if you can see it or hear it, but it's there and it feels good to me. Cross bolts are torqued, and I can finally move on. I've got the blocks spun up now so we can install the odd side pistons and rods, and I've seen something which reminded me of a previous comment. I did a video tearing down this disaster of a 426 Hemi a few weeks back. I mentioned that it's got sleeves in all 8 cylinders, and for that reason it doesn't have the intake valve notches. My understanding is that those notches are factory equipment. Every 426 Hemi block should have had that. A commenter said, no, that's not factory, and people just added that for racing purposes over the years. Are you sure about that? Because these notches sure look factory to me, and the factory type steel shim gasket is made specifically to go around them. Remember, I'm no 426 Hemi expert. I certainly don't know everything there is to know here, and I've only had my hands in like 4 or 5 of them at this point, but my understanding is those notches are supposed to be there. There's actually another Chrysler RB engine that had that same feature, and that would be the Max Wedge, because it also used gigantic valves. Piston rings installated. I used to spiral these into place by hand. I've taken heed to the warnings in the instructions lately that say don't spiral them in by hand. I spiral in the oil control rings now, but generally I'll spread these with a pair of pliers and carefully slot them in where they go. Now it's time to pop some rod bearings in here. I noticed that our machine shop replaced the factory rod bolts with ARP stuff, and that's great. I'm sure they have a good reason for doing that. They did the same on our 440 build over here. It's important to note that the ARP bolts, studs, whatever the heck you want to call them, have their own special torque spec. It's 75 foot-pounds with the ARP lube. They actually advise that you use the stretch method to check your tightness here, but I don't have a stretch gauge, so I'll just be using the 75 foot-pound number. Now, I noticed when looking at these rods that a good few of these bolts were not inserted all the way. That's interesting because to resize the big end of these rods, that is, hone them back to the factory dimension, they would have had to have been torqued with these new ARP bolts. Well, it turns out the reason they were like popped out is because you've got a super tight press fit between these and the rod cap. So to get the rod cap back off, much like the main caps, takes some doing. It's not a press fit between one bolt shoulder and the cap, but it's pretty close. It's a very tight fitment. And if there's any spacing difference between these, well, obviously that's gonna lock this thing in place super tightly. Thankfully, we don't have any goofy loose fit on our rod bearings. These snap right into place and fit perfectly. I gave all of the bores a final cleaning wipe down, and then I applied a little coat of engine oil to help installing our pistons and rings. I did the same to the ring compressor tool, and on the advice of Just Mopar Joe, I bent those little tips out at the bottom. Hopefully that'll keep this thing from falling down into the bores as I'm installing the 426 pistons. The internet is a silly place to exist sometimes. In one of my recent Engine Wednesday videos assembling an engine, someone told me that I should put little lengths of rubber hose over the studs or bolts in a rod when installing them. That can help guide the rod around the crank and keep the bearing shell from popping out, which happens sometimes. I've explained in past videos that not only do I do that, I use a loop of hose which goes up around the crankshaft, connects to both, and gives you something to help guide it down as well. But of course I didn't do it in that particular video. Things get lost in translation sometimes. It is what it is. There's one piston and rod installed. The rod is carefully down on the crank. Here's the cap. You'll notice the notch goes out toward the oil pan rail on this side and matches with the notch in the rod. There's the number one cap popped in place. It's amazing how easy installing it was compared to trying to work it off of the rod out of the engine. Now I need to get some ARP lube on here, and then I'll just snug these down for now. When I'm done installing all 8 rods, we'll torque these to their final spec. And there are the rod nuts snugged down. When you're lubricating these fasteners, make sure you get a healthy amount on the threads, but also under that head surface. Look at that beautiful shiny dome piston. Tell you what, this thing spins beautifully with just the one on there. At this point in the broadcast, I'd love to calculate the compression ratio here. And I have almost everything I need to do that, except a good reference point for the compression height. Now the problem is, on a Hemi piston, the compression height is below this dome, and there's no flat area to measure it on. So doing math with this, even though I have the CC of this dome from the manufacturer, would be, I'm not gonna say impossible, but challenging. I don't know what order these projects are going to be finished in, so I don't know which video you're going to see first. But on this 440, I actually did hand calculate the compression ratio. I'm not going to do that for the 426 Hemi. If that's a subject you're interested in, see the second build video on this 440 with the stealth heads and all of the fancy doodads. No, what we're going to do here is just assume it's fine and run premium fuel. Yeah, best technique for separating the rods and the caps is to leave the nuts loosely on those bolts, then smack them with a dead blow hammer or something with a soft face till they come down enough that the shoulder is out of the cap. Then the cap pops back off, and all you got to do is tap these back home. Here's your bi-weekly reminder to wipe out your new bearing shells, because they're almost certainly going to be full of fiber and fuzz. With that little modification on this engine, unlike that 440, that just popped right in. You always got to make a blood sacrifice on builds like this one. That was almost a major one. 2 pistons in now, and this action is still like butter. Odd side pistons are done. And there we have 8 happy Hemi pistons. Yay. I've got all of the rod nuts torqued to that 75 pound-feet number now, and it still spins nice, so that's a good sign. Camshaft time. This is a regrind of the original 1971 and 1970 Hemi hydraulic lifter camshaft, at least according to this box. So I measured it, and the numbers I came up with are really close. Of course, I was using the world's crappiest measuring equipment, so it's not 100% precise. The specified lift is 490 intake, 481 exhaust, and I came up with 486 intake, 474 exhaust, but that's pretty close. Note, the intake and exhaust rockers on a Hemi have slightly different ratios. It's 157 for the intake and 153 for the exhaust, so that's how I arrive at these numbers. To measure lobe lift, of course, we zero this crappy digital caliper on the base circle, and then measure the difference between that and the top of the lobe. This thing's like dying, and well, it sucks all the time. So yeah, this may not be the most precise thing in the world, but it's close. Now, it's easy enough to identify a Hemi camshaft compared to a normal big block one. Only Hemis, 6-barrel cams, and then some aftermarket cams use this 3-bolt drive for the cam gear. Note, this has a full grooved number 1 cam bearing journal. That's a special Hemi thing. And also the number 4 journal is fully grooved. That's the one that feeds the oil up to the rocker shafts. Now, I have no idea who ground this cam, but I do know I had to clean some nasty varnishy oil off it. It's been in this box for a very, very long time. With that done, it's time to apply some lube. I'm going to use the Lucas assembly lube as I did on the last one, and then the journals will get engine oil. Camshaft is in, which is very easy to do when your Mopar block is upside down and you can just reach through and guide it through those holes. Spin test. Yeah. I had to dig out the cam gear bolts. I've got one of those in, so this thing sits on the pin and I can spin the cam. I've got the crank at TDC, and now we are aligned dot to dot. I'm gonna put the chain on that way, and then I suppose we'll degree this camshaft. Timing chain is on now, marks are aligned, and here's the slop we've got. Here's one of our new lifters. I need this to degree the cam. These are Johnson high lifts. They're not brand new. They're new in box from 2016. They look pretty good, and supposedly Johnsons are worth using, so we're gonna run them. These are special for the Hemi and the 446 pack engines. The crown is a little bit different to match the different taper of the lobes. Now, to degree a camshaft, you take your measurements off of the intake lobe. If this was a B or an RB engine, the valve order and therefore the lobe and lifter order would be exhaust, intake, intake, exhaust. But because this is a Hemi, the valve order is intake, exhaust, intake, exhaust. And we can tell pretty easily which pushrod and therefore which lobe is which here by the positions of the pushrod holes. The exhaust holes actually go through the deck surface so they can reach over to the super long exhaust rocker. In case you were suspicious that your Hemi cam is not a Hemi cam and you wanted to double check, well, right now I've got this thing at overlap for cylinder number 1. Intake is here, exhaust is here. Because we're at valve overlap, that means the intake is just starting to open and the exhaust is just closing. This is our intake lobe, and you can see, because this turns clockwise, this valve is just coming up while the exhaust valve is just going down. So again, we can tell that way this is a Hemi cam. If it wasn't a Hemi cam, those events would be reversed. It's a little while later, and I've got good news and bad news. The good news is I'm learning more and more about how to use a degree wheel, and I'm going to share what I've learned with you. The bad news is that is not a 1971 Hemi cam. Now, the specs are very close. I actually did get a lift number, and it's 0.313. Now, that's total lift from the base circle to the top of the lobe. I measured duration at 50 thou tappet lift at 229 degrees. And the way I did that was find 50 thou lift on the ramp up and then on the ramp down of the intake lobe, and then comparing those two numbers. 108, 109, somewhere right in that range is the center line. But 229 degrees is the duration at that 50 thou lift number. Now here's where things got a little weird. I really wanted to demonstrate how to measure the duration of your camshaft, both the advertised and the 50 thousandths number, which is a lot more useful. You tend to see both of those in a listing for a given cam. So I tried to find the zero lift position, and I marked that with this long bar. And then I went around to the other side of the lobe and did it a second time. Here are those two marks. Now, we can count the number of hash marks, the number of degrees between the two marks, and if we subtract that number from 360 degrees, we'll get a total duration number. Okay, the problem with that is we've got a 30-degree spread between these two numbers, which would indicate a duration at zero tappet lift of 330 degrees. That's a lot. Like a lot. And I've already measured at 50 thousandths and we've got 229 degrees, which is pretty mild. According to the factory service manual, the Hemi cam should have had a duration of 284 degrees. 284 is much less than 330. So what gives there? You don't know what you don't know. And I didn't know at this juncture, in fact, I still don't know, at what tappet lift Chrysler measured their factory duration specs. For that reason, the correct spec did not match what I was seeing at all, and I started to think this might be the wrong type of cam profile. I thought this might be a camshaft that was designed for solid lifters, which would explain the extra duration. So I went on a quest to figure that out, and I ended up putting the old cam back in this engine to measure that and compare. It's a long time later, and I've learned two things. First, this cam is literally exactly the same as this cam. And second, don't know how the factory measured duration, but the numbers I'm getting are nothing like the factory duration specs for this cam. I am fully confused. There's nothing quite like thinking you're onto something, going out of your way to learn, then wasting hours being wrong and humbling yourself in front of thousands of people on the internet. Anyway, our new old cam is back in, and we never need to talk about this again. Well, the good news is we've confirmed this timing gear and its dots are accurate, and this thing is installed at 108 degrees. It's a while later, and some things have happened, which I didn't bother showing you because, well, I don't know. The timing cover is on. I did have to install a new front crankshaft seal. There's a new paper gasket behind it as well. We've got cleaned up factory bolts here. They actually ended up mixed up in the bags. The timing cover bolts were in the oil pan bolt bag, and the oil pan bolts, well, 6 of them were in the timing cover bag. Anyway, that's all sorted out. And those are snug down, and I'm happy with it. I've got the special gigantic 426 Hemi harmonic balancer installed. I use the actual tool to do that. Oftentimes I'll install these with the bolt, but you know, Hemi. Let's do it the right way. I had a problem on the 440 I'm building at the same time as this thing, where the balancer ended up flush with the crank snout. Notice, we don't have that problem on the 426. In fact, this is like a 3/4 inch gap. Evan that works here at Rocket has a ton of hours into cleaning and sandblasting parts. The balancer, obviously, the timing cover, this harmonic balancer bolt washer, which is special on the Hemi, you can see it's super thick, was done. The head of the crank snout balancer, whatever bolt was not done. I think this ended up going to the machine shop, actually. Anyway, I did have to take a break to sandblast that and clean it. And now this can go in and get torqued to spec, which I think is 135 pound-feet? I don't remember. It is indeed 135 foot-pounds. Have you noticed I've switched between saying foot-pounds and pound-feet multiple times in this video? That's so everybody will be either pleased or annoyed or both. And I went ahead and torqued it properly instead of giving it the Uggy-Duggy treatment, which I usually do. Again, because Hemi. I wedged the crank in place for the torquing like so. And I bent a perfectly good screwdriver. Other things that have happened, the rear main seal cap is in. Of course, the lower half of the seal goes in this aluminum dealy bob. We had to change this from the one that was in it because someone had installed the wrong oil pan bolt at some point, and these holes were actually blown open into the engine. This is just a nice looking stock piece, obviously. Now, I used a Felpro crank seal for this thing. The side seals on this actually are random new old stock ones I found in our stash here. They're not rubber like the Felpros, they're kind of like fiber, I think. I did supplement them with, let's say, a good bit of silicone though. The special Hemi oil pump tube is in. I did apply some sealing tape right here to the threads, and I verified that this height is correct using our shiny new oil pan. This is the new pan, it's the Hemi style one. It doesn't have a part number on it, as you can see, like most big block pans do, and it's got the big gigantic sump. It also has baffles. I think these reproduction pans are made by Hoffman. I could be wrong on that. I don't actually see the 70 and up pan on their website. I see it on various sites. All you need to know is multiple companies can get you these and they're not made in America. I didn't know Brewers Performance sold engine parts, but apparently they do. Here's the Hemi pan for $200 on their site. They list this as a 6-quart pan. I believe it's a 7-quart total fill. The same pan was used on 440 HPs in 1970 and 71. We're installing one on the 1967 440 I'm rebuilding currently. We also put one of the same pans on the V-Code 6-pack engine I rebuilt. We're installing this oil pan factory style because Hemi, we want it to look right. That means laying down 1 quart gasket, then the factory steel windage tray. It goes in there as a sandwich plate. Then another quart gasket goes below that, and then finally the pan. Now I am going to go ahead and slightly coat all of this with silicone because I don't really want it to leak, and I will be coming back through and retorquing the pan probably 3 or 4 times. For some reason, I cannot find the windage tray pan that came out of the 426. It's not with the oil pan and pickup. We actually have a bunch of these in stock, and I'm sure we have a good one somewhere. I found an NOS pan in the pile of parts, but it's for a stroker crank. We're not going to use that for the Hemi. I found this one, but it's total dog crap. So yeah, I'll have to dig around back there and find a good one, clean that up, and then we can install the pan. In the meantime, this one can go there. Oh, hey, was now a good time to realize that this is the wrong timing cover and the timing mark is off by like 10 degrees? I happen to know that Hemis and regular big blocks use a slightly different timing mark. I don't know why that is, but I do know that if we take this number as gospel and try to tune this thing, we're going to have a bad time. And I sure am glad I realized that before I had an oil pan on here buttoned up. We're not ready to have cylinder heads like actually installed, so this is not official, but you know I had to do it. Look at it. It's beautiful. But wait, there's more. Intake, valve covers. Nice. It's so hard to imagine anything cooler than a 426 Hemi. Just seeing it all put together like this, the width, the massiveness, it's the stuff dreams are made of, and I'm excited again. But yeah, I really gotta go, so we will revisit this in a future Engine Wednesday. Hopefully at that time we're like buttoning it up, priming the oil system, dropping it on the run stand, and hearing awesome Hemi noises. Till next time, as ever, thank you very much for watching. And remember, they don't call it the elephant for nothing.